Hello, IEEE ANTEM 2021. I am Amir Bahadur Mansouri, and in this recording, I'm going to present our paper, which is Design of Short Backfire Antennas for Remote Sensing Applications by Amir Bahadur Mansouri and Dustin Slavson from the University of Manitoba, Department of Electrical and Computer Engineering. This paper has been submitted to the student paper competition as well. This presentation includes 5 sections. I will start off by talking about background and motivation and the importance of this paper, and answer the question, why is this research important? Next, I'll talk about the design concepts and different parametric studies and design considerations. Then I will explain the antenna fabrication process following with the antenna measurement results. Eventually, I'll wrap up my presentation by talking about conclusions and future work. And in the last slide, I'll show you the references that I use for the presentation. In summary, we present design, simulation, and measurements for a waveguide fed C-band short backfire antenna that has been developed for remote sensing applications. All the performance metrics were achieved in the principal planes, and we were able to demonstrate good agreement between measurement and simulation. Over 50 years ago, Ehrenspec invented the short backfire antenna, which is a compact topology and can be used when medium gain is required. These antennas have different applications and can be used as Wi-Fi antennas or for satellite communications. An example of their application is the directional antennas used in the Apollo missions, facilitating point-to-point communications. Recently, antennas have started to be mounted on unmanned aerial vehicles, or in short UAVs, for remote sensing applications. They need to be low profile, low mass, and highly efficient. These UAV systems provide a way to test the hardware that is planned to be used on the satellite systems. And the short backfire antenna is an excellent choice due to its past space heritage and the fact that it can be designed to meet the requirements. Therefore, our goal was to design a C-band antenna, which is the same frequency as the RadarSat constellation mission with a low number of parts. As discussed before, the designed antenna needed to be low profile, low mass, and be able to handle a high amount of power. By now, I've discussed the motivation and the importance of this work. Now, I want to talk about the design concept and important parameters in this design. This antenna is comprised of different sections, including a main reflector, subreflector, rim, and a waveguide for feeding. As I mentioned earlier in my talk, we plan to design an easy-to-build C-band short backfire antenna, the same frequency as RadarSat-2, and use it for remote sensing. For the design purpose, I used HFSS simulation software and excited the antenna with a waveport. I performed different parametric studies to find out the best dimensions of the design. In the remaining slides, I will show you some of the results of the performed parametric studies. As you can see, the design metrics are shown in the upper right table. The goal was to design an antenna with realized gain of greater than 14.5 dBi, bandwidth of 500 MHz, and cross-polarization ratio of greater than 25 dB. After performing different parametric studies on the diameter of the main reflector, diameter of the subreflector, height of the subreflector, and the waveguide length, I came up with the dimensions which are shown in the lower right-hand side table. I need to mention that the height of the rim of 0.6 times lambda was selected based off of Professor Shafai's previous work. In this slide, what you see is the results of one of the parametric studies. In this study, I altered the diameter of the subreflector to see its effect on the antenna realized gain at different frequencies. This figure shows that changing the diameter of the subreflector or operational frequency result in a change in the antenna realized gain. As you can see, for the subreflector diameters greater than 0.3 times lambda, the realized gain of all frequencies starts to increase, and the increase has a steep slope. For lower frequencies like 4.5 GHz, the curve reaches its maximum at 0.5 times lambda. On the other hand, for higher frequencies such as 5.5 GHz, As we increase the frequency, the maximum realized gain shifts to higher diameters like 0.65 times lambda. After performing all the parametric studies and finding the best dimensions, we started the fabrication process. The antenna components, which are shown in the right-hand side figures, are 1 6-inch section of WR159 standard waveguide, an SMA to waveguide adapter, and the antenna main body, which consists of a main reflector and a subreflector. Two antenna prototypes are shown in the middle and left-hand side figures. As you can see in the middle design, we have used a foam material to position the subreflector at the specific height, and in the left figure design, nylon posts have been used. I need to mention that the proposed result in this paper are related to the middle configuration, which has a foam material. In order to test the antenna performance, we started to measure the antenna reflection coefficients, and for this purpose, we used an Agilent N5224B vector network analyzer, or in short, VNA. The first set of measurements showed a small frequency shift, and therefore we decided to add two copper strips to the waveguide aperture to create an inductive iris for matching purpose. We investigated the width of the strips in HFSS simulations and found out that 4 mm gives us the best matching. In the left figure, you can see the antenna, which is attached to the VNA, and the right figure demonstrates the results of simulation and actual measurements. As you see, measurement results and simulations are in good agreement and follow the same trend. There is only one deep notch at 4.1 GHz, which is because of the subreflector alignment, which probably is not completely parallel to the main reflector. Well, after the S11 measurements, now it's time to measure the antenna radiation pattern. The antenna radiation patterns were measured in the University of Manitoba's Compact Antenna Test Range, or in short KDR, and the measurement setup is shown in the left figure. Once the measurements were done, we compared the measurement and simulation results. There was great agreement between the measurement and simulation results in the principal planes. As you see, the peak measured copolarization in the E-plane radiation pattern of short backfire antenna is 14.53 dBi and is 0.18 dB lower than that of the simulated. The peak measured cross-polarization level in the principal plane is -21 dBi, and the worst-case cross-polarization, which occurs at the diagonal plane, or more precisely at phase equal 52 degrees, is -1.99 dBi. To conclude this presentation and wrap up, I would say that we designed and verified a C-band waveguide fed short backfire antenna. There was great agreement between the measurement and the simulation results, and all the performance metrics were met in the principal planes. A summary of the actual measurements and the design matrix are shown in the table for the reference. For future work, we will investigate the cross-polarization at other planes, and by adding a choke and modifying the surface current distribution, we plan to improve both the impedance bandwidth and the realized gain simultaneously. Professor Isleifson, Professor Shafai, and I have already written a full manuscript that addresses some of these issues, and you can check it out. Finally, we would like to thank and acknowledge NSERC and the University of Manitoba for providing funding for this research, CMC Microsystems for the provision of CAD tools, Mr. Corey Smith and Mr. Hassan Zainali for fabrication and test of the prototype SPF antenna, and Professor Lutfullah Shafai for insightful discussion. And here you can see the references that I used for this presentation. Thank you again for listening, and I would be happy to answer your questions.